Is it possible to reverse time by changing the rotation of the Earth? In the 1978 Superman film, Superman, the Man of Steel, decides to swoop into space and travel counter-rotationally around the Earth in order to reverse time and save his most beloved Lois Lane, who died of a tragic death. Now let's go back to the question aforementioned. Is it really possible to reverse the Earth's rotation by flying around it? Of course not. And the reason for this can be easily summarized by the phrase, "Give me something to stand on, and I will move the Earth," intoned by the famous ancient Greek physicist Archimedes. This just means that in order to move the Earth, you will need a firm spot to stand on, to support your weight, and to gain leverage. Also, this relates back to Newton's third law of motion, that when object A exerts a force upon object B, there is an equal and opposite force acting upon both objects. In the clip shown in the beginning, Superman clearly does not exhibit applying a direct force upon Earth. Therefore, it is impossible for him to move Earth just by flying around it. So instead, Superman just repeatedly jumps and falls back to Earth like in this clip, so that he can apply a direct force upon Earth. But, how much force is needed to cause the Earth to rotate the other way around? In order to answer this question, we need to use the concept of angular momentum on a spinning object, and that we assume Superman does not travel around the globe, but rather applies a force on a single point on Earth, which we chose to be on Toronto. First, we're going to solve for angular momentum. Angular momentum is equal to the moment of inertia times angular velocity. The moment of inertia for Earth is equal to 2/5 times the mass of the Earth, 5.98 times 10 to the 24 kilograms, times the radius squared, 6.4 times 10 to the 6. And we multiply that by the angular velocity, which is 2 times pi divided by 86,400 seconds, which is equal to 1 day. When we plug those values into our equation, our result is 7.12 times 10 to the 33 kilograms meters squared per second. Alright, so now we're going to solve for the force applied by Superman on the Earth. Force is equal to T over D, where T is torque and D is the distance from Toronto to the axis of the Earth. In this case, it's the North Pole. But first we have to solve for torque. Torque is equal to the angular momentum divided by time. So we have 2 times 7.12 times 10 to the 33 divided by 60. And our result for torque is 2.37 times 10 to the 32 kilogram meters squared per second squared. So now we could solve for force. Force is equal to the torque over distance. Our torque was 2.37 times 10 to the 32, and our distance was 4.7 times 10 to the 3. And then our result for force applied by Superman on the Earth is 5.04 times 10 to the 25 newtons. From the clip, after Superman stops accelerating, 8 seconds after he begins traveling, he starts to go 2 revolutions per second around Earth. And since the distance of Earth's circumference is 40,000 kilometers, then the speed of which Superman is traveling is around 80,000 kilometers per second. But this doesn't affect him that much, since there is less pressure or more space between the particles the closer you are to space. But how fast can steel travel through air before friction produces enough heat to melt it? And since Superman is supposedly made of steel, he has a melting point of around 1,510 degrees Celsius. Thus, he mustn't move with a speed higher than 70 kilometers per second, otherwise he would start to liquefy. But if he were to continue traveling 80,000 kilometers per second, we can calculate the heat he experiences by taking the ratio of Superman's top speed around Earth and the fastest speed of a meteor that can travel through the atmosphere at 72 kilometers per second. And then the ratio is 1,111 to 1. Then we can multiply 1,111 with the temperature of which the meteor is subjected to, and we get that Superman experiences a tremendous heat of 1.8 times 10 to the 6 degrees Celsius.